Welcome to my mycodelab channel. Today in this video we are going to cover boundary traversal of binary tree. So what we are given in the question, we are given a binary tree and we need to traverse it like a boundary traversal, like we need to cover boundary nodes of that tree. You can just read it from here, what it actually means, what I'm trying to say. Right, let's see example. You have to traverse like this because 1, 2, 3 are boundaries of this tree. Right, let's see one more example. In this example we have to output 1, 2, 3. We need to go anti-clockwise like 1, 2 and then 3. In the next example we are given this tree and we need to return this 28, 4 and then 10, 14 and then 25, 22 and we have already covered 20 in the first, so we are not going to take it again. So yeah, it will only print till 22. See this diagram. We have to go like this. There is one more interesting edge case you can consider. Suppose this node have a left node, so we need to follow it till we get a node where we don't have any left and child, any left and right both, like this. 4 do not have any left and right child, so we have to go till we get node like this. If we have node at the right part here, then we have to move like in DFS manner till we get our first node which have no left and right part both. Same we are doing for the right. Actually this problem can be tackled in 3 parts. We call it a sub part. First one is we have to consider the left part and all the leaves, and then right part. Right, in the left we have to go from top to down. In the left we have to go like this, and in the right side we have to go like down to top. So we have to tackle this problem as a 3 sub problems. We can just take all these 3 sub problems value in 3 vectors and then merge all the vectors according to our question into a result vector. Alright, so let's solve this problem. So we can apply a DFS for left side. We can also apply DFS for leaves. We can also apply DFS for the right part. Right, so we are given with the function name is print boundary. We are getting parameter called root, which is of type node. Here is the definition of structure node, which has data of integer type and 2 pointers pointing left and right side of the node, and we need to return vector which will contain our output in desired form. Like we have to traverse a tree in a boundary manner in an anti-clockwise direction. Okay, so let's solve this. So now let's declare a vector. I think it is visible. Okay, so just declare vector result, vector of integer type result where we are going to store all our result, and we are also going to declare 3 more vector where we are going to store their values separately, and then after that we are going to just merge all those 3 vectors into one vector called result. So we need a left part, we need leaf, we need right part of the tree. Okay, so we also need to store the address of the root, because in DFS we are going to lose it and we are going to assign it again. So declare it pointer of type node called store assign 10 root that we are getting from here. Okay, so now we are going to perform the left part. DFS. Okay, we need a stack in DFS. If you are familiar with DFS of type node, we are going to name it S1. We are going to run a while loop till root is not equal to null or stack is not empty. Okay, we are just going till root is not null, and we are just going to push back our values into the left part vector. Okay, left part we have declared here. Now we need to go one step ahead in the left direction, or we can say to the left side of the root. Okay, now at this point the root will be pointing to the null, so we need to get the address of the last node processed. Actually, we also need to push values in the stack, right? That is why we are using stack. So we can just get a value of the last process node from the stack, and we are going to pop it, and we are going to check if root left right is null. You can simply assign it to the root left. Okay, if root, so it is our simple DFS, but it is going to store all the element. Oh, we are doing mistake here. So it is going to store all the values of our tree, but we are just required to get the left side of the most left part of the nodes, right? We don't need all the nodes, so we need a break condition here. So what is the break condition? We have to break whenever we get a node where left and right both are null. So as you can see, the all elements here till here have a child on the left side. If it comes out of it, then it may have child on the right or may not have a child on right. So we just simply need to check it. If root equals to null, we just need to break. right, or we can just use this also if root, because root is storing root left. Here it should be right, because we have to go right, because there is no left, so we need to go right. So yeah, it is done. This part is storing all the left node that we require into the left part. Left part is the name of a vector where we are storing all the left part node, right? Now we need to store leaf. We also need to DFS again. So yeah, root assign store, because we have lose the real value of the root. That is why we have declared stored and use it, right, to assign it back. So again, right, what we can do is we can just clear stack and just copy the same code. Why to write same code again and again if we have here? Just change this part. Just remove this part and also this part, because here we are considering we are going to loop all the element, but we are just going to store only those values which have no left and right part. That is the definition of leaf. A leaf don't have any left or right child. So yeah, we are doing here simple DFS, but with the one valid condition for our desired output, that is if right is equals to null, and then root left equals to null. Then we are just going to push back into the leaf, back, but we have to push back the root's value. Okay, so yeah, we are done with the leaf part. Now we need to do consider right part. DFS, we need to apply DFS again. Root assign store. We can just paste that code again because it's almost same. We just need to change one thing. Here we have in the right part, for the right part we need to go right instead of left, right, and we also need to change the vector name where we are storing data. It should be right, not left. Okay, so yep, we are going to right, so here we have to go left, and yep, if it is not, we have to break. If we reach to the point where there is no left and right child, then we can break. Okay, so now we have all the three things, that is right part, that is the values in the right part. Yep, we have forget the one thing here, to clear our stack before performing right. Now it is okay. We have values in leaf, we have values in left part. So now we just need to combine all this value into the result so that we can return it, right? So yeah, int len if left part dot size is greater than 1. Size greater than 1 means simply means it have root and one more element at the left side. So if this is the case, then we are just going to ignore the last element, because we are going to consider the last element into the leaf, because otherwise it will come twice, in the leaf and in the left part as well, same as we will do on in the right side. I will just explain you, don't worry about it. Len equals to left dot size -1, because we need to, else len equals to len assign left part dot size. Okay, now for int I equals to 0, I is less than len, I plus plus result dot is back left part at I. Okay, now we need to combine the leaf part, merge leaf. So we have to consider whole leaf. There is no problem with leaf, like equal 0, I is less than leaf dot size, I plus plus result dot back leaf at I. So it is leaf. Now we are going to merge right side, right part. Okay. In the right part we need to go from the reverse side, from bottom to top. Okay, so it will be like if right part dot size is greater than 0, it is greater than 1, it means that it has more than one value. So we need to ignore the last value and the first value. Okay, we also can do one thing here in the right side. We can use this statement after this, so that it will not going to store the roots value. It will just perform the right part and then it will store at root. But this is not the valid, because it may have null and data may contain no value. It will throw error. So here we can just make a check here. Simply, if it is greater than 1, then it means that it has more than one element. Then what we can do is we can say that len equals to right part of size minus 2. Okay, no, minus 1, else len equals to right part dot size. Okay, now for int I equals to len, we need to start from len. Actually it will be minus 2 because index start from 0 and we are assigning I equals to len. So if we are just assigning the size minus 1, then it is just a last element, so we need to minus 2. For this it must have two values. Right, I is greater than 1. Why 1? Because we are not going to consider the root. Okay, we can set it 0 because root is at 0 and I minus minus. Now just result dot is back to the right part at index I. I think we are done. Right, now return result. Okay, so it is a simple problem. We have just wrote 3 DFS. 2 DFS are efficient, we are breaking, we are not performing till end, and 1 DFS is whole. We are traversing all the node, but we are only considering the node which have both the child of node left and right child of the node are null. Okay, so let's see if it is working or not. Let's compile the code. Oh, so yes, so we have to use different stack, or we have to just clear empty the stack. So yes, we can use empty like while s1 dot empty while it is not true. It gets true when stack becomes empty. Okay, so what we are going to do, s1 dot pop. This code we have to run in place of s1 dot clear because it is not a function here, I think. So we can just simply replace it with this simple code. Yep, I think it will work now. Oh, pops is a function, so it will have parentheses. How can I forget it? Okay, so 1 2 3 and it is printing something else as well. Right, so I think here we are doing some mistake in merging the right part. If size is greater than 2, if size is less than equals to 2, then we are just assigning size, and it should be 1. So here we were assigning a len equals to right part dot size, and right we have to minus 1 as well because we are taking into the consideration. That is why it was just throwing out of bound. Now it should work. We are printing 3 one more time. Why? We are printing root again. I think it should I greater than 1 because yes, it is working. We can submit. Wrong answer. Okay. What is wrong? 4, 10, 5, 6, 8, 1, 3, 5, 8, 6, 11, 11, 1, 3, 7, 5. So we are just adding something extra which should not be there. Like so we can just check our right part. We are storing data here. We are going left. We are breaking here. Seems to be right. Okay. If it is less than 2, then we have to do nothing. Okay. If it is greater than 2, then only we have to do something. Like we need to why? Because in the left part in the right part we are just ignoring this and this as well. So if it is only 2, then we have to ignore this and this as well. So we have to do nothing until it is greater than 2. So this is why we are doing this. Now it is going to work again. Let's see. I hope it will work. Again spelling the same test case. Y needs 7, 5, 10. Why? Okay, so we were missing only one case, that is a corner case too. Like if we have this tree and suppose there is no 22 and 25 node, I mean there is no right child for the root, then what we were doing is like we were coming to the right and see it is null, then we were popping from the top, and top is storing a root that it will store 20, and then we were checking if root left is null or not. If it is null, then only we were breaking actually, but in this case it is not going to be null. You can see, because if it points to 20, then left will be 8. So it was taking extra this. That is why we need to take we need to add one more condition, that is if root is equals to the actual root, that means root equals to store. Either this condition satisfies or either this condition satisfies, we need to break our loop. We need to apply this in both where we have applied this, I mean right part and on the left part as well. Right, we are not applying in the leaf because we are traversing whole. In leaf we are not breaking, we are just taking consideration only the node which have this condition, its right is equals to null and root's left is equals to null. We are only considering this, but we are looping all the nodes in the tree. Okay, so let's submit this code again. Okay, it got accepted. So yeah, if you like this video, just break that like button, and if you want more videos like this, then hit that subscribe button.